So in this simulation, I can add up sinusoidal time graphs whose frequencies are multiples of some basic frequency. So this red graph is the one with the lowest frequency or the longest period. And if I increase this slider here, what you see is that in the second panel, there's an orange graph whose frequency is exactly double the one corresponding to the red slider. Or the period of this orange one is exactly half of the one corresponding to the red graph. And so what you notice is that when you add the two up, regardless of how much of the orange one I add, then the graph at the bottom, which is the sum of these two graphs, that has exactly the same period as the original graph. And we can understand that because every time the original graph repeats, the second graph repeats twice. And so then the whole pattern repeats with the same period as the original graph. We could also add a third graph with 3 times the frequency, or 1/3 the period, and we're still going to end up with a graph that repeats at the same period as the original graph. So we could keep adding different amounts of these time graphs whose frequencies are perfect multiples. So 2 times, 3 times, 4 times, 5 times, 6 times the frequency. And in the end, what you see is that you get a periodic graph, but now it doesn't look very much like a nice sinusoidal graph anymore. So the other thing that this simulation allows us to do is to hear the sound that this time graph corresponds to, if we think of that as the displacement graph for a sound wave. And so what we've learned is that a periodic time graph should sound like a musical tone with the frequency corresponding to the frequency of the graph. And so because the frequency hasn't really changed, then this graph that we've got here in the end, it should still sound like a musical tone. It should have the same frequency as the pure tone that we started with. So let's have a listen. Okay, so that is the combination of all of these tones. And at least to me, that just sounds like one note, even though you might think it would sound like a whole bunch of different notes with different frequencies all playing at the same time. Because these are perfect multiples of one frequency, our brain actually combines them into one particular tone that has a different timbre from just a pure tone. So I'm going to play that one more time, and then I'll also go back to the pure tone with that frequency so you can hear the difference. Okay, so here's the pure tone. Okay, and so you see